Swayam Prabha. Digital India. Educated India.
Okay, so we have seen the multiplicative inverse modulo n or modulo some integer n. So, now we will talk about how to find that inverse. So, suppose let n be a prime, no, n be an integer, then we have seen the and a is also an integer, be an integer. Then we have seen if a is relatively prime with n, that means GCD of a and n is 1, then we have seen a as a inverse. This inverse in the multiplicative sense, multiplicative inverse mod n. So, that means there exists a b such that a into b is congruent to 1 mod n. Then this b is called a inverse mod n. So, this is what is the multiplicative inverse of a under multiplicative inverse of a modulo n. So, in this lecture we will see how we can find such b, how we can find the inverse a inverse. So, that is basically coming from the Euclid algorithm, but we have to extend it little bit. Euclid algorithm will give us what? GCD of two numbers a b. So, this is basically how we define the inverse of a, and for existence of inverse we know that this is basically this a must be relatively prime with n, and so we need to know how we can find the inverse. So, this is basically how to find the inverse a inverse. So, this is basically coming from the Euclid algorithm. We know the Euclidean algorithm. So, Euclid algorithm is basically finding the GCD of two element a b, two integer a b. So, how we can find the GCD of two integer a b? Suppose a is say 41, b is say 54. Now basically Euclid algorithm is basically GCD of a b is same as GCD of a comma b mod a, if b is greater than a. So, this is the theorem we have proved, and based this theorem is basically the Euclid algorithm. This theorem will give us. So, these are the remainder. So, then we take this remainder with a like this. So, this way we continue. Okay. So, basically so we can, if we take this example, then basically if we try to find out GCD of 41 54, then this is basically GCD of 41 54 mod 41. Okay, now 54 mod 41 is how much? 54 mod 41 is basically 13. So, then again we take this like this, GCD of 13, then 41 mod 13. This is because we can, this theorem GCD of AB is basically GCD of BA. Okay. So, anyway, so this is basically, so 41 mod 13 is basically 2. So, GCD of 13 comma 2. Now, again we will write like this GCD of 2 comma 13 mod 2. So, this will give us basically 1. So, GCD of 2 comma 1. So, this is basically 1. So, GCD of this is basically 1. Okay. Now we will prove a theorem where GCD of AB can be written as GCD of AB should be written as AX plus BY for some integer X and Y. So, this is a theorem, we need to prove this, and this is basically will give us the this X give us the extended Euclidean algorithm. So, now for this example, how to get this x y? So, basically to get x y, we will just so GCD of this is 1. So, 1 must be written as. So, in our example, if we take A is equal to 41 and B is equal to 54, then just now we have seen the GCD of 41 and 54 is 1. So, that means we must get 2 x y such that this should be written as 41 x plus 54 y. So, x y are 2 integer. So, how to get such x y, that is the question. Okay, so, to get x y, we have to just follow the Euclid algorithm that remainder, then we will go back like this. So, let us try that. So, this first we are finding the 54 mod 41. So, that means that is 13. So, 54 will be written as 1 into 14 sorry 1 into 41 plus 13. Okay. So, that means GCD of these two is basically same as GCD of 41 and 13. Then again 41 should be written as then the 41 mod 13 is basically 2. So, 41 should be written as this plus 2. Okay. Again 13 will be written. Now, we need to find out the this is the Euclid algorithm. So, now we need to find the GCD of this 13 and 2. So, this is basically 6 into 2 plus 1. So, now we need to find the GCD of 2 and 1. So, this will give us 2 into 1 plus 0. So, that means this last step will tell us the GCD is basically 1. Okay, now to find the x y, we just ignore last step, we got already 1. So, we will just reverse this. So, how we can reverse this? So, from this equation we can write 1 is equal to 13 minus 6 into 2. Okay. Now, 2 is basically 41. So, we will just convert this side by only 41 and 54 and remaining are x or y. So, that we will try. So, that is basically the extended Euclidean algorithm. So, this 13. So, this 13 minus 6 into 2. So, again 2 will be written as 41 minus 3 into 13. So, 41 minus 3 into 13. So, if you multiply this, so this is 18 and 1. So, 19 into 13, this is into minus 6 into 41. Now, from this equation we can write 13 as 54 minus 1 into 41. So, that we will write. So, 19 into 54 minus this is minus 1 into 41 minus 6 into 41. Okay, so, this is basically 19 into 54 and this is minus 19 and minus 6. So, this is basically minus 25 into 41. So, this is basically 54 into 19 plus 41 into minus 25. So, this is our x and this is our y. Okay. So, this is the example where any GCD is here 1. So, 1 is written as this 54x. Yeah. So, this is this 19 is y and this is x is minus 25. Okay. So, now we will prove this formally by a theorem. This is through an example, but this we will prove by a theorem. So, let us state that theorem, and that theorem will give us the extended Euclidean algorithm to find the GCD. Okay. So, to find the inverse, sorry, Euclid algorithm is to find the GCD, but the extended Euclidean algorithm will give us the. So, this is the theorem. Theorem is telling the greatest common divisor or the GCD greatest common divisor of two integers a and b can be written as ax plus by for some integers x and y. So, that means GCD of AB should be written as ax plus by for some x y. So, this is the theorem. We have to prove this theorem. So, this proof is coming from the Euclid algorithm, those remainder sequence of the remainder. So, how to prove this? Okay. So, basically to prove this we will compute the sequence x0, x1, x2 so on and y0, y1, y2 and so on, such that the remainder is basically axk plus byk. So, these are coming from Euclid algorithm basically, where remainder coming from Euclid algorithm. So, where this R0, R1, R2 are the sequence of remainders in Euclid coming from Euclid algorithm. Okay. So, in Euclid algorithm we start with A and B. So, basically what we have R0 is equal to A and R1 equal to B. This is the initial case, and x0, y0 is basically 1 into 0 and x1, y1 is basically 0 into 1. So, that means we can just check it. So, R0 is basically A, which is basically A into 1 plus B into 0. So, this is basically A x0 plus B y0. This is the initial case. We will prove by induction. R1 is equal to B, which is basically written as A into 0 plus B into 1, which is our a into x1 plus b into y1. Okay. And for other than 0 and 1, for I greater than 0, what we do? We set q I plus 1, that quotient is basically r I minus 1 by r I. So, this is the division step, and r I plus 1 is basically r I minus 1 minus r I into q I plus 1. Okay. So, the r I plus 1 is the next remainder. So, r I plus 1 is the next remainder. Okay. So, now what we set from this general case, we have to set x I and y I. So, we set x I plus 1, we set x I plus 1 is basically y I minus 1 minus x I q I plus 1, and y I plus 1 is basically y, sorry, this is x I minus 1, and then this, and y I minus 1 minus y I q I plus 1. Okay. Now, we have to show by mathematical induction that r k is basically a x k for such k plus b y k for all integer k, for all k. So, this we have to prove by induction. Now, this for k is equal to 0 and 1, this is true, because that was the base case. Okay. So, now we will prove this by induction. Now, for k is equal to 0 and 1, it is true, and this is the base case. So, for induction mathematical induction is having base case. So, we need to prove that some properties with n, natural number n. So, for that we prove that this statement is true for n is equal to 0 or n is equal to 1, and then we show that if the statement is true for n is equal to k, then we show that statement is true for n is equal to k plus 1, then the statement is true for all natural numbers. So, that is the one, that is the method of induction hypothesis, induction method. So, now we assume the statement is true for k is equal to I minus 1 and I, and then we will show the statement is true for k is equal to I plus 1. So, this is the induction hypothesis or the assumption. What is the assumption? We assume it is true for k is equal to I minus 1 and k is equal to I. So, that means r I minus 1 is basically a x minus 1 plus b y minus 1, and r I is basically a x I plus b y I, and we have to prove that the statement is true for k is equal to I plus 1. So, for k is equal to I plus 1, what is r I plus 1? R I plus 1 is basically r I minus 1 minus r I q I plus 1. Okay. So, now we put the value over here. So, this is basically a x I minus 1 plus b y I minus 1 minus r I is this one. So, a x I plus b y I into q I plus 1. Okay. So, this we can write as like this, a x I minus 1 minus x I q I plus 1 plus b into y I minus 1 minus y I q I plus 1. Now, this we know, this is basically x I plus 1 and this is basically y I plus 1 plus y I plus 1. So, it is true for, so this implies the statement is true for k is equal to I plus 1. So, hence this statement is true for all k. So, by the mathematical induction, so that means this implies r k is equal to a x k plus b y k for all k, for all natural number k. And so, this ri's are basically the remainder, and slowly, so by Euclid algorithm slowly we will eventually we get, when we stop, when we get the remainder is 0. So, eventually by Euclid in the Euclid algorithm, eventually we reach r n plus 1 is equal to 0 and then the previous r n is the GCD basically, and r n is basically GCD of a b, which is basically a x n plus b y n. Okay. These ri's are basically, so we are running the Euclid algorithm. So, it will stop when the remainder is 0, then the previous remainder will give us the GCD, and that remainder is always in this form. So, we will maintain this x k y k. So, finally, so this is basically x, this is y. So, GCD will be written as a x plus b y. Basically, it is x n y n. So, this is the proof of that any GCD can be written as a x plus b y. So, this will give us the extended Euclidean algorithm, which we just every time we maintain this x k and y k. So, finally, we have this this x y. So, once we have x y, so if the GCD of, so we will come how to get x y by Euclidean algorithm. So, just we follow these steps, we will have a algorithm form, we will see that. So, now if suppose we have two integer, let a and b be two integer or x and say b and m, b and m be two integers such that GCD of b and m is 1. So, that is they are relatively prime. So, b is relatively prime with m. Okay. So, that means we have proved the theorem. So, that means this there should exist x y such that 1 is equal to b x plus m y for some integer x and y. So, this x y is basically coming from the when you run the Euclid algorithm. So, this remainder every time we write the remainder in x k a this b x k plus m y k. So, finally, eventually it will end up with the remainder 0, r n plus 1 is 0, then the previous remainder is the basically the GCD. Okay. So, now so now we have this form. Now, from here we know this, then x is basically b inverse mod m. So, this is the multiplicative inverse. So, if we can find this from x y, if we can find x, then x is basically the inverse multiplicative inverse of b under modulo m. So, that we will get from the Euclid algorithm. Okay. So, let us talk about this Euclid algorithm. So, so here is the algo version of Euclid algorithm. So, basically what we have how we have the theorem proved. This is the steps basically. So, we want to find the B inverse mod m if inverse exists, provided GCD of m, B and m is 1. So, provided B is relatively prime with m, then the B inverse mod m exists. So, this is basically B3 basically give us the GCD. Okay. So, what we are doing initialization step, we are taking help of some temporary variable. This Ai's we are assigning 0 1 0 m and B's we are assigning 0 1 b, and we run this until B3 is either 0 or 1. If B3 is 1, that means this is the GCD is 1, otherwise we return no in, then B2 will give us the inverse. So, we will see this B2, B3, B3, and we have a temporary variable q, which is the basically quotient, which is the A3 by B3, and this is also 3 temporary variable. We are taking this value A1 minus q into B1, A2 minus q into B2, A3 minus q into B3, and then we copy this A1 B2 A1 A2 A3, that this B1 B2 B3, and B1 B2 B3 is now replaced by T1 T2 T3, the new value of this temporary variable. Then again we go to 2. So, until the B3 will become 0 or 1, we will continue these steps, this loop. Okay. And so, this is the pseudo code, this is the code for finding the GCD basically. So, once we got the GCD is 1, that means B3 is 1, then the B2 will give us the inverse. So, B2 is basically the x. So, we are maintaining x over here. So, this B2 will give us the x, this x. So, finally, this is B3. So, if it is 1, then GCD will exist. So, this is B2. Okay. So, now let us this will work, because it is every time we are maintaining this, we are trying to store this is the every time it is B small b into B2 is 1 minus m B1. So, B2 is congruent to 1 mod m, and every time we are maintaining this B2 is equal to 1 minus m B1. So, 1 is equal to this. So, in other words, we are trying to find the B1 B2 that solves the equation this 5. Okay. And so, this is the temporary variable, and throughout the algorithm this T1 T2 T3 are the temporary variable, and this is the way we are replacing B1 B2 B3, and throughout the algorithm this relationship hold. Okay. So, basically we are trying to get x and y. Okay. So, finally, if B3 is basically 1, that means GCD is 1. So, then the B2 will give us the inverse. So, here is an example. Suppose we want to find the suppose this is B, small b. So, we want to find the multiplicative inverse of 550 modulus 1759. So, this is basically our m, small m. Okay. So, what we are storing this value like our algorithm. So, this value is basically A1 is assigned 1, A2 is assigned 0, and A3 is assigned basically m, and B1 is assigned 0, B2 is assigned 1, and B3 is basically assigned B. This is the initialization step, and Q is basically A3 by B3 every time. So, Q is 3, and then we are just changing this value by this temporary variable, calculating temporary variable A1 minus Q B1, A2 minus Q B2, A3 minus Q B3, and that will be replaced in B1 B2 B3. So, this will we continue until this B3 will become 0 or 1. If the B3 is becomes 1, then the GCD is 1, and the corresponding B2 is basically inverse of that B inverse mod m. Okay. So, this is just the execution of this code of this will give us the first. Basically, we are doing the Euclid algorithm, and finally, we are getting the GCD. So, now if the GCD is 1 and every time we are maintaining this x and y. So, x and y, because that RK is basically a x k, a is different here. So, b x k plus m y k. So, every time we are calculating this RK. Okay. Now, eventually this R n plus 1 is 0. So, that means R n will give us the GCD of b and m. So, if R n, so this is, if R n is 1, then the GCD is 1 and the corresponding, this is b 2, we are storing this value, then the corresponding this value is basically b inverse mod m, provided this is provided GCD is 1. So, this is basically the we are executing the Euclid algorithm, but every time we are storing this x y. So, that we can get the inverse of b, provided the GCD is 1. Thank you.